increases up to here, because here I have a decrease of the turbine flow, because the natural flow of the Po River is lower than the design flow. So I have a max of production here. Then I have a decrease of flow. It's true that there is increasing head, but the increase in head doesn't compensate the decrease in flow, and therefore I have a decrease of energy production. So what is shown in the figure is also an energy production curve which looks like this. Looks like something like this. With a max here. So I think this figure that you find on my webpage is interesting, so have a look at it. Keep in mind that the max is not necessarily located here, because the increase in head could compensate the decrease in flow, but this doesn't happen in this plant. So indeed we have the max here, the max at the duration of the design flow. And also, this figure is a bit tricky, because this is called in the figure, it's called power duration curve. I don't think we can call it a power duration curve, it's misleading. This is a curve that says for each duration, and therefore corresponding flow, what is hydropower production. For each duration it gives to me the hydropower production. But instead of saying for each duration, I prefer to say, because it's clear, for each river flow through the associated duration. Just spend some time trying to study this because it's interesting. Okay, now, before I think we can stop, and let's take 5-7 minutes for questions. And as I said, you are obliged to ask at least 2. Okay.
I have a question about that picture. The dashed line is the river path.
Yeah.
Yeah, when there is a high flow, right?
So, let's suppose that there is no plant. If there is no plant, this is the river path, and then that's it. Okay, when instead, let's suppose now this is a canal, and in order to make the figure clearer, I think I should identify also the river as a canal. This is the correct figure. So basically what happens, when you have, also there is a gate here. So what happens, when you have a flow that is lower than the design flow or up to the design flow, what they do is they close this gate and open this gate, and everything flows through the hydropower plant. They take care of monitoring the quality in the meander, because what happens basically is that, keep in mind that the meander doesn't get empty, because here you have a water elevation in the river that is about 15 meters, and the difference in elevation here is about a couple of meters. So it means that water from here can flow back, and therefore what you see at this gate is a difference in altitude between upstream and downstream, but doesn't get empty. But the moral of the story is that you don't get any flow here. So they take care of monitoring the quality, and if they see that the quality is decreasing, they release some flow.
So that gate is necessary for this to work?
Yeah, this is necessary, because otherwise, you know, you would have the same water level here and here, and some water would go anyway along the river. So you need this gate. Then what happens is when you have flood flows, they could open everything, because of course you cannot get flow higher than this QD through the canal. You would have an overflow here. So they could open everything. Actually what they do is they close this gate because they don't want to get the canal silted by sediments. So during high flows they just close this and open this and leave the water flowing as in the natural conditions. So the dashed line was just something that I depicted for saying something. I don't remember what I said, but it's not really water path. Okay. Second question.
Yes. So in the flow duration book, I mean, how can you take like QM from there?
How can you take?
Sorry, how can you like put QM in the where to put it? I don't know. I'm doing the
QM?
yeah QM.
No, I didn't put it. I
Yeah,
just said, yeah, but if I tell you where I
okay,
will put
okay.
it, it's, the question is lost.
Another question is
No,
that
let me say, we can discuss it, but not now. I just wanted you to think
yeah,
about it.
absolutely, okay.
Okay?
And another question is that I didn't understand really good the difference between QM and QMP.
Okay, perfect. So QM is average flow in pristine conditions, which is something that is not related to what you are doing. You estimate the flow duration curve and you get QM. What is QM? Is the area below the flow duration curve divided by the duration. So this is a flow by definition, because the area is a volume, you divide the volume for the duration and you get QM.
Is a full volume like
Yeah, full volume of the flow duration curve, full volume. And then you have the volume of withdrawn flow.
that is like the orange part.
Yeah, the orange part, yeah. And I already said that QM is higher than QMP. So this is already an indication for you. If I asked you, can you please put two lines here, two horizontal lines, because QM and QMP are average, so they are constant along the duration. So if I asked you, please put two horizontal lines for QM and QMP, I already told you that QM should be higher than QMP. Okay? And there is a very simple way to place QM. Because QMP is difficult, because you know environmental flow, etc. This volume that is to be mirrored. QM is very simple. It's just based on the flow duration curve. Other questions?
Excuse me?
Yeah.
The reason of the curve that we've made on the graph is that we can't instantly take exactly that amount of water.
Yes, you mean the orange part?
The blue one.
The blue one?
Yes.
No, this is environmental flow, okay? So this is something that we release and we cannot take. So
Yes, but where is its curve? Isn't it the...
this one? This one? Because there is a curve here. I mean, just 1 second, because I want to make sure that I didn't make a mistake, sorry. No, that's fine. Okay. Basically, here you should release environmental flow, everything, the whole of it, because otherwise you don't have a surplus of water with respect to QD, an excess of water with respect to QD. But here you start getting an excess of water, and this excess of water basically means that you can decrease your amount of release for environmental flow. When you get to this point, you have an excess of water with respect to QD that is precisely the amount of the environmental flow. So you can just close the gate of the environmental flow. Yeah, it's something that you have to think about. Okay.
So is the volume, just the small volume under the curve, is the same of the upper small volume?
Same volume, yeah.
And those are the calibration volume?
No, not calibration. It's just, this is a volume that is automatically determined because I place here the value of the environmental flow.
Okay.
And then the volume that is comprised by this abscissa of the environmental flow, flow duration curve, and design flow. This is a volume that has to be mirrored here. One thing that is not clear to me is whether the convexity is, because this is to be mirrored.
Yeah.
So I think probably the convexity may be the other way around. So the convexity may be...
Because
Yeah,
we have to complete the
Yeah, just think about it, because
Okay.
it's just a matter of subtracting. Basically, you have to take for each duration, here for instance, you have this abscissa, and you have to subtract it from here. And then you get your position on the curve here. And then you go for the other duration and you always subtract from the environmental flow what is the excess flow with respect to the design flow. As I said, it's something that is not easy to teach, but it's very simple. It's just a matter of summing and subtracting. So think about it, and if there is something that you don't understand, we can discuss later. Okay? Other questions?
Is 15-20% a standard value in designing hydropower plant?
As I said, it's a rule of thumb, and you know, it depends on the local conditions, on the cost-benefit analysis that I mentioned in the previous blackboard. But anyway, you can take it as a rule of thumb, not as a strict rule. Okay. Okay, good, perfect. Thank you. Sorry for the technical problem.